Hi, yeah, this is Dan Isaac. I'll be presenting today some of the work that we've been doing in association with Bonneville Power Administration the last few years. And the idea here is basically to use and pull together large interagency um, data sets on juvenile fish surveys for Chinook salmon and steelhead, and use those in association with spatial stream network models and a series of geospatial covariates to describe habitat relationships for these two different species. And so other collaborators on this work were Aaron Peterson and Jay Verhoof, who've done a lot of the SSN model work with us over the years, as well as then folks at our Forest Service lab here in Boise, Idaho. And so just for a little bit of context and background, um, you know, everyone's familiar with the fact that we do a lot of aquatic monitoring in the Pacific Northwest, and we've spent literally millions of dollars collecting fish density and occurrence information from thousands of sites across the region. And as extensive as those data sets are, that they're still, oftentimes represent drops in the bucket compared to the full extent of the stream and river networks that we have in the region. And so it would be nice to be able to use those site observations to fit models that could then make reliable inference about what may be occurring with regards to species distributions or abundance trends, status, etc., over these larger river networks. And that was quite difficult to do until Aaron and Jay kind of put their heads together a few decades ago and developed these spatial stream network models that work particularly well with these sorts of non-random data sets that show a lot of spatial clustering once you start bringing these data together from multiple agency sources. And these SSN models then are developed specifically to account for network topology, the directionality of flow, and then also the sorts of spatial autocorrelation issues that pop up in these sort of aggregated data sets. And so just out of curiosity to see how well these types of models would work with typical fish survey data sets, we published this paper a few years ago, just based on 100 or so electrofishing site surveys in a small river basin on the border between Idaho and Wyoming. You see those sites in the left map there. Fit the model to it, and then use the model to basically predict throughout the full river network then densities of trout, and then also get estimates about the spatial precision of those predictions. And we saw a pretty good increase in the predictive performance of the models when applied to data sets like this. That scatter plot of predicted versus observed densities on the left there is just developed using a standard multiple linear regression model that doesn't account for spatial autocorrelation in the data set. The scatter plot on the right then shows that same data set fit with the SSN model. So we get a big predictive boost from using and accounting for spatial autocorrelation in these data sets. And so the idea here was just to apply that at a larger scale with a larger data set that maybe people would be more interested in, because it starts to have practical implications once you start doing this stuff at a large enough scale. And so this is the work that BPA funded us to do, basically pull together all the juvenile fish surveys collected via electrofishing and snorkeling from CritFic, ODF&W, Idaho Fish and Game, ICEMP Biomark, and Forest Service across this relatively large portion of the interior Columbia River Basin. So we've got here the John Day represented, the Grand Ronde from Northeast Oregon, as well as the Clearwater and Salmon River basins within Idaho. And so two species that we're focusing on then are Chinook salmon and steelhead. And for both of those then we've got in excess of 6,500 site years of data. So big fish survey data sets to work with. And the first thing we did then was to link those observations of abundance at those sites to reaches within the National Stream Internet Hydrography dataset that's based on the NHD Plus medium resolution dataset. And so to obtain that, we simply went to the NSI website, downloaded the streamlines, made that linkage. And then because those medium resolution networks still show a lot more streams than these two species actually use within the study area. We had to trim back those networks to represent the potential network of suitable habitats. And for that, then we relied on the StreamNet species distribution data sets. And for the most part, those worked pretty well, but there were sites or instances where we had observations of these two target species in streams that were not designated as habitat for these two species. And so in those cases, then we extended what StreamNet has in their database for the distribution of these species. And those extensions then are represented by the red lines within each of those maps. For Chinook across this area, then there were about 9,000 kilometers of potential habitat, whereas for steelhead there were about 18,000 kilometers, so about double that for Chinook. And then these are what the data sets look like when visualized on those networks. And here we're just looking at what the counts or population estimates were from the different agencies translated to number of individuals per 100-meter length of stream. And then it's just color coded based on low densities in blue colors up to higher densities in red colors. And so you can kind of see what some of the spatial patterns look like there for Chinook and steelhead. And so next step was then to have a series of covariates that we would link into the site observations. And the only limitation here was that these had to, for the most part, be available as geospatial data sets that occurred everywhere within these stream networks. Because after we fit the model to the observations, we then want to use it to make predictions throughout the full river network. And to do that, we need to have these covariate values available everywhere. We won't go through all of these, but just kind of the general categories of things that we looked at were things like stream hydrology characteristics, stream temperature characteristics, underlying geology, land use, land cover types, road density, whether brook trout were abundant at a site, et cetera. There's a lot of different things that are available nowadays. And we pulled these generally from U.S. Fish and or U.S. Forest Service data sets such as Norwest and VIC, or the NHD Plus StreamCat data sets, or the Natural Land Use Cover database. And then there are also a couple different additional nuisance covariates that we include in addition to those spatial factors in the previous slide, one of which was just the interannual variability in density or abundance, because there is obviously a lot of variability in the number of adults that are coming back to these systems each year, and that translates to juveniles. So we just included a year effect with the average densities associated with that in the model. And then also the agency source of the data, because each of these agencies has a slightly different protocol for how they collect their data sets. And so we just include that as a categorical variable in the model. The model structure is just a linear model like the SSN models always are. It's just only thing that they do that's different from a traditional, say, multiple linear regression is that they have a spatial error function to recognize and deal with spatial correlation in the residual errors. And then model selection, basically just a three-step process. We fit the original model with the full set of covariates. Because these are large data sets and these SSN models are computationally fairly complex, it took about 6 days for a big workstation to run that original model fit. And so after we got the results back from that, we then looked at the significance of the variables, dropped those that were not significant, and then refit the model using that reduced set of covariates. And then kind of twiddled our thumbs for another 6 days while the model fit again, and we got a final set of results. So once we fit the models, we can then make predictions for abundance at a site relative to observations, and these scatter plots are just summarizing that. For juvenile Chinook, we could account for 57% of the variability at those 6,757 site years of data, and for steelhead, not quite as good, but still about 50% of the variability. Overall, these aren't hugely accurate predictive models, but at the same time, they're pretty good given all the different inconsistencies that go with these data, and they're also comparable to what we saw in our earlier pilot study where we had just a consistent trout density data set collected using multiple pass electrofishing. So I was actually pretty pleased by these results. So the model, once that's done, then you can use it to represent the response curves, or that describe basically the habitat relationship associations in the model. And for juvenile Chinook, these were the 7 variables that were statistically significant and showed up in the final model. Basically, you've got that year density effect that accounts for the interannual variability. You've got brook trout density, reach slope, mean August stream temperature, mean summer flow within a reach, so stream size essentially, repairing canopy density, and base flow index. Those were the 7 variables of those 28 or 30 that we described earlier that showed up as significant in the final models. And kind of the take home from all those things in is, the model suggested that juvenile densities for Chinook were highest in medium-sized, cool streams with low gradients and intermediate amounts of canopy and base flows. So, pretty well matches kind of, I think, the general perception of what this fish prefers that's out there in the literature. For steelhead then, these are the response curves for the variables that showed up as being significant in the final model. I'll note that 6 of the 7 variables here are the same as they were for the Chinook model, but the form of the relationships differs. So for example, if you just focus on reach slope there on the left side of that graphic, and I'll just flip to the Chinook model, you can see that response curve for the 2 species is very different, with Chinook preferring low gradient reaches and steelhead preferring kind of intermediate gradient reaches. The take home, when you summarize across all these response curves and this composite set of predictions from the model, are that juvenile steelhead densities were highest in small, warmer streams with intermediate gradients in canopy and greater proportions of conifers within the watershed. And so again, pretty well matches, I think, what the general perception is of what this species prefers that's out there in the literature. So that was encouraging to see both of these 2 models kind of representing the ecology of these species. So then once we fit the model to that set of covariates, and we've got those covariates geospatially represented everywhere within the stream network of potential habitats, we can use the model to create kind of a standardized scenario and make predictions throughout that full river network from the observation sites. And this then is what we call scenario 1, which is the average densities of juvenile Chinook over this period of 2000 to 2018, where we had the data submitted by the agencies for this project. And here again, then we're just displaying these densities from low density to high density, kind of along a heat map scale. So places that are blue have low densities of Chinook on average, and places that are yellow, orange, and red have higher densities. And if we look at this for steelhead, same sort of thing, but they've got, again, a much denser or larger potential habitat network within this geographic area. And again, then just representing their densities under this scenario 1 kind of baseline as a heat map. An interesting thing about steelhead is because their thermal niche and their response curve suggests they prefer streams that are a couple degrees Celsius warmer than Chinook. We see kind of a big disparity here from east to west in terms of where the highest densities of steelhead show up within this network. Basically, Oregon has warmer streams and higher density steelhead. Then you get into Idaho, higher elevations, a lot colder streams, and a lot of those streams right now, the model is predicting are too cold to really be optimal for high densities of steelhead. And so we created then, after that baseline scenario, an additional set of scenarios representing each individual year within this study period from 2000 to 2018, We've got a scenario in there that also represents the spatial uncertainty in the predictions from the model. And then we've got three scenarios that represent kind of future climate change scenarios. So, if stream temperatures were to increase by 1 degree Celsius, 2 degrees Celsius, or 3 degrees Celsius, what would that look like in terms of predicted effects on these two species? And so you can use that then for various things. All this information is available as geospatial data sets. And so, for example, you could take scenario one and subtract that from scenario 23, which is based on a 2 degrees Celsius warmer, map out the places where Chinook are predicted to increase in abundance or decrease in abundance. And here we can kind of see what the results of that look like. Essentially, some of those really cold streams in Idaho are actually predicted to become more suitable for Chinook. Those are colored green. And then a few places, say in Northeast Oregon, that are already pretty warm are predicted to become too warm for Chinook and then densities to decrease in the future. Same thing for steelhead, just looking at kind of that climate sensitivity analysis by subtracting the baseline from a 2 degrees Celsius future warmer, and it shows a lot of those streams in Oregon becoming even better in terms of thermal suitability for steelhead, and then kind of a scattering in Idaho of some streams also becoming a little bit better for steelhead in the future as it gets warmer. Another potential application of this, and something that BPA has been interested in, is using these maps that kind of represent what the actual densities are on the landscape with their modeled representations of intrinsic potential. And so, how much would there be under kind of restored conditions that you can, again, these are all geospatial, so you can subtract one from the other to try to identify and maybe be spatially precise about where you would target restoration actions going forward. Kind of the take homes from this research, firstly, ecologically realistic models were possible to be created with decent predictive accuracy using SSNs and these large interagency data sets that were pulled together for this project. Those modeled scenarios and fish survey data sets are formatted as ArcGIS shapefiles to provide functionality for additional analyses, as I tried to highlight in the last few slides, and for communication among partner agencies. Just having a consistent map data format that everyone can work off of oftentimes facilitates discussion. The GIS covariates and model relationships that are used in these models, they're not very good at representing land management and local habitat alteration effects. They just don't have that level of resolution that you need to really pull out that sort of local habitat alteration. This SSN approach is scalable. You can simply add more data and more fish data and refit it for new areas using these geospatial covariates. Or in the absence of that, you could just apply these existing modeled relationships and the parameter estimates with covariate values to kind of expand the predictions that way. And thirdly, you could also explore creating new models using other data types like eDNA, water quality parameters, habitat surveys, temperature, etc. Because this whole national stream internet, SSN models, big data sets, that's all just kind of different modules of one overall framework that works consistently together. And there is some potential to kind of semi-automate some of this as well. And lastly, then, just for folks that are interested in accessing these data sets, the ArcGIS shapefiles of these density scenarios are available at the StreamNet data store. You can go to that link, and there's also then a BPA report that describes in more detail the results and data sets that are available at my ResearchGate profile page. And that's all I've got. Thank you very much.